Hello everyone and welcome to chapter 4. In this video I'm going to be discussing the concept of solutions and what all does it take to make a solution. And so to begin with we have to start off with some good old-fashioned definitions. And so in order to be classified as a solution, technically what you need to have is some type of, and I say in this case salt, but again some type of solid normally is dropped in some type of liquid. And so in these cases, one of the main definitions that stipulates that this mixture must be homogeneous. And so homogeneous means it must look exactly the same all throughout the entire mixture. And so another one that you're probably more familiar with is making Kool-Aid from the little packets of Kool-Aid. And so in this situation, you take the Kool-Aid, you pour it into the water, and if you don't stir it up, you do not have a homogeneous mixture. You have some sections that are red and some sections that are not so red. And so here you have to stir it up in order to get what they define as a solution, a homogeneous mixture. And so a solution is created by two different components being mixed together. The first one that I kind of, again, quote unquote, changes state, or the one that begins as a solid and it ends up looking like it disappears. And so in the example of table salt being dropped into water, your table salt is going to be the solute. Whereas in the example of Kool-Aid, the sugar packet that you are putting into the water is going to be the solute. And so normally with most of the problems you'll be seeing throughout this chapter, the solute is going to be the solid that you are putting into the liquid. And so normally by a looser definition, a solute is also known as the component or the substance that's going to be in lesser quantity in this mixture. Or on the other end of things, we have the solvent. And so again, typically for the remainder of this chapter at least, or for the remainder of these videos that have to do with this chapter, the solvent is going to be the liquid. Water is a great solvent, mainly because it's everywhere, in addition to some topics or some concepts I'm going to bring up on this next slide. And so the liquid is going to be the solvent. The solid is going to be the solute. The solution is what is created when you mix a solvent and a solute. I apologize for the naming system. I did not create it. And so you need to be familiar with what a solute is versus the solvent because it's going to come up a lot during this chapter. And so before I can actually go a little bit further into talking about these solutions, we have to talk about an issue that arises whenever things are shared unequally. And in things, in this case in particular, are electrons. And so if you have a diatomic molecule, diatomic element in particular, and so in diatomic elements, you have two atoms that are exactly the same. N2, F2, O2, H2, all the diatomics that I've discussed in the past. And so in these types of compounds, you have two atoms that are exactly the same. And whenever I say exactly the same, I mean they have the same atomic size, same electronegativity, they form the same type of bonds. And so in this situation, everything is equal between those two atoms. And so because everything is equal, there is no cheating or kind of stealing some of somebody else's electrons. But if you were to replace one of those atoms with something else in the other atom that has a different electronegativity, then you're going to be looking at an unequal sharing of these electrons. The example I show here is HCl. And so one thing you need to remember about hydrogen is composed of one proton and one electron, no neutrons. And so in order to create a bond between the hydrogen and the chlorine, you are going to have to share an electron. And so hydrogen only has one electron and it's willing to share that electron with chlorine in order to make this bond. Where chlorine, on the other hand, has 7 valence electrons, meaning the fact you still only need one electron in order to share with hydrogen to make that bond. But whenever it shares that one electron, it still has 6 other electrons that it's not going to be sharing. Meaning in this region around the chlorine right here, you're going to have a whole lot of electronegative portion versus nothing on this side because remember, hydrogen, 1 proton, 1 electron. Its electron went into this bond, so all that's really left in this region of the molecule is just a proton. And so 1 proton on this side, 6 extra unshared electrons on this side. In addition to that, chlorine is much more electronegative than hydrogen is. And so even though hydrogen and chlorine are both contributing 1 electron into the center to make that bond, what's really happening is chlorine is kind of stealing a little bit more of that sharing electron than hydrogen has a chance to. Don't worry, hydrogen doesn't mind, but again, chlorine is not sharing very equally here. And what happens due to that fact is you end up with what they refer to as a partial positive region around this hydrogen. And you have a partial negative region around this chlorine. And so please note, I am saying partial positive and partial negative. I am not saying that H becomes an H plus and that Cl does not become a Cl minus. It is still an HCl molecule. It is still neutrally charged. But in the instances of electrons, there's an unequal distribution of electrons around that hydrogen and that chlorine. There is less electrons around the hydrogen. There's more electrons around the chlorine. Or if we kind of expand this view to water. In water, you have your oxygen. And again, we'll talk about all this stuff in the later chapters, like chapters 9, 10, 11 and so. But around oxygen, you have 2 lone pairs of electrons, or 4 electrons that are not being shared. And so in the instance of oxygen, you have a partial negative charge around the top portion of the oxygen. But again, these 2 hydrogens down there acted very similar as they did in the HCl. You have a partial positive charge around this hydrogen because it gave it 1 electron to form the charge or form the bond. And so all that's really left around the nucleus is just a proton, similar to this hydrogen. The reason why all of this matters is if you include a solute that is also charged, that means that this sodium plus and this chlorine minus, after you drop it into water, is going to be attracted to different parts of this water molecule. In addition, if you had liquid HCl, this Na plus would not kind of be hanging around this hydrogen because it's a positive charge. This sodium plus will not hang around these hydrogens because it's a partial positive charge. Sodium is a positive ion. Positive and positive don't get along too well. But on the other end, if you have this chlorine with a negative charge associated with it, it's more than happy to hang out in this positive region. So typically what happens whenever you have an interaction between your ionic complexes and water, you have a battle going on. And so, will it dissolve? That is the main question you have to ask yourself when you're thinking about taking solid ionic complexes and dropping them into water. And so in this situation, remember, the whole idea of an ionic complex is you have an attraction between positive ions, negative ion, positive ion, negative ion, so on and so forth. So we call that a solute-solute interactions. So one more time, solute-solute interactions occur between the solute. It is the attractions that hold that solute together. But as soon as you throw this into water, you are now looking at solute-solvent interactions that could also occur. And by those, I mean sodium plus ions being attracted to water's oxygen, and chlorine minus ions being attracted to water's hydrogen region. And so in these 10 purposes, you need to make sure that you understand what the difference is between solute-solute and solvent-solute. Once you got that down, you just have to ask yourself, which one is going to be stronger? And this is going to be discussed much later in the chapter, so a few videos from this one. But the whole idea here is if the solute-solute interactions are weaker than the solvent-solute interactions, this complex is going to be dissolved. These ions are going to be completely separated from one another once you place it into the solvent. And so, salt water. The reason why we say salt dissolves is because as soon as you take sodium chloride, even just one tiny crystal of table salt, and you drop it into water, that sodium chloride is going to be ripped apart from every end by this water. And the reason for that is because sodium plus and chlorine minus, they are very attracted to one another when they are on dry land. But as soon as you put them into water, they start to realize that there are other options that you can kind of hang out with. And so as soon as you place sodium chloride into water, the solute-solute interactions are not strong enough to overcome the solute-solvent interactions. And so in this situation, sodium chloride now becomes sodium ions and chlorine ions. And so one more time, as soon as this salt enters water, there is no such thing as NaCl anymore. They are completely dissociated. These ions are completely separated from one another. And so all you have left is ions. No NaCl, all Na plus Cl minus. And so please note the way I have these water molecules facing, the Na plus is going to be attracted to this oxygen region or the partial negative region. The Cl minus is going to be attracted to this partial positive region or the hydrogens on your water molecule. And this happens to such an extent that every single ion in this table salt is going to be ripped apart by this water. And as soon as that happens, you actually have other water molecules kind of join in and completely surround this ion. Same situation with the sodium ion. All the water molecules completely surround it. And so at no point, as long as this water is involved in this situation, are Na plus and Cl minus ever going to rejoin and become table salt again. The only way that this can occur is if you just get rid of all the waters through evaporation. And so that's the only chance that this Cl minus is ever going to be able to join back up with this sodium plus in order to create this overall ionic complex again. And so, on the note of talking about ions that are completely separated from one another, this brings up another definition of electrolytes. And so an electrolyte is a substance that can be dissolved into a solvent that can give you free ions. And because you have free ions, this thing is able to conduct electricity. Whereas other substances, if you pour them into water, no matter how much you pour in there, it's never, ever, ever going to conduct electricity. And the reason why this works is something like table salt, as I mentioned a few times by now, splits up into Na plus and Cl minus ions. And so in this solution, that's all there is. Remember, no more solid salt. All the salt will completely dissociate into the separate ions. And so in this solution, you have Na pluses and Cl minuses and Na pluses and Cl minuses, and that's all that's here. And so as soon as you hook this battery supply up, you'll have this Na plus kind of hanging out over here. It sees this negative electrode, and so the Na plus is going to go over there and look at the electrode. And as soon as the Na plus gets a little too close, it picks up an electron and again becomes sodium for a half a second. But again, sodium plus doesn't want to be sodium. It's in water. It wants to be sodium plus again. And so as soon as it picks up its electron, it cruises over here to the other electrode and says, here, you have this. And the same deal with the next sodium plus. It gets attracted over here, picks up an electron, goes over here, drops off the electron. And goes back over here, picks up another electron, drops it off. Same deal with chlorine, but in reverse. Chlorine's going to go over here, back over there, so on and so forth. And this is how you are able to conduct electricity. The transfer of electrons from one electrode to the other. Electricity. But if you have something like sugar, sucrose, glucose, fructose, any of the oses, those are all organic substances. Those contain carbons, hydrogens, and oxygens that are covalently bonded to one another. And it's something that I try to stress in my previous videos. Covalent complexes cannot contain ions. Those are two opposite extremes of the situations here. And so if you have an ionic complex, it splits up into ions. If you have a molecule, all it does is just become smaller and smaller and smaller and smaller versions of that molecule. But sucrose and fructose and all the other sugars, they're always going to stay in the exact same molecular shape, size, formula, everything else. Because you cannot create any ions in here, you don't have any pluses, you don't have any minuses, there's nothing to carry charges around. And so all you're going to do here is just make a lot of sticky mess, and that light bulb is never going to turn on. And so the next idea that's very useful for this whole concept of free ions is if you know the chemical formula. So if you know the chemical formula for your solute, you know the ions that are going to be produced. Not only that, you also know the exact number of the ions that are going to be produced. And so a few kind of notation notes here. First thing is if you see H2O or if you see anything written above your reaction arrow, all that really means is that this is going to be KBr solid plus water to get to this next step. And so I just want to kind of throw it out there. Again, you could just write KBr solid plus H2O, but sometimes you might see it a little fancier way of writing it, in which you just put whatever the reaction is going to be involved is going to be on top of the reaction arrow. Secondly, aqueous, 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 aqueous. Aqueous just means floating around in water. And so if you have an ion or if you have a substance that completely dissolves, you would write it out as aqueous to imply the fact that it, again, ions just floating around. And so if you take solid potassium bromide and you take this and you place it into water, and please note, I'm talking about it initially as solid, you place it into water, you are going to produce K plus ions in the aqueous form and Br minus ions in aqueous form. Please note, this has to be a 1 potassium to 1 bromine ratio because in the chemical formula there's 1 potassium and 1 bromine. Whereas on the next one we have CaCl2. Again, starting off at solid, placing it into water, and we know we are creating a calcium 2 plus ion because that's the common ionic charge of calcium that is aqueous, and 2 of our chloride ions. And the reason why we have to have 2 of our chloride ions aqueous is because we start off with 2 of our chlorines inside of our CaCl2. Remember, all ionic complexes must be neutral. There must be the same number of pluses as there are minuses. And so we need to make sure that still applies even on the other side of the chemical formula. Here we have a calcium 2 plus, so we need to have 2 of our chloride minuses in order to cancel this overall charge out to end up with 0. This next one, I just wanted to point out more particular the fact that polyatomic ions stay completely intact. And so when I first introduced these guys a few videos back, I mentioned the fact that you need to treat these as a single entity. And by that standard, I mean you are not going to take solid sodium hydroxide and place it into water to produce sodium and oxygen and hydrogen. Because OH is going to be a polyatomic ion with an overall charge, it has to be treated as an ion. And so here you would take this, you would place it into water to create sodium plus ions and hydroxide ions, both in an aqueous solution. This still applies to your carbonates, to your acetates, to your phosphates, to your sulfates. All of them will remain exactly the same way they appear in the chemical formula. And so next thing we have to kind of check out is a practice problem. And so how many moles of each ion are in the following solutions? And so this first one I give you is 78.5 grams of cesium bromide with a molar mass of 212.8 grams per mole dissolved in water. And so from there, using our old school math and some of our dimensional analysis that we've hopefully done plenty of practice of by now. If you haven't, please do some more practice. You need to get very efficient at these. They're not going to go away. And so we start off with our 78.5 grams of cesium bromide, and we're interested in figuring out how many moles of each of these ions are going to be present. So the first thing you need to do is be able to convert cesium bromide words into chemical formulas. And so cesium is in our group 1, so we know it's going to have a +1 charge. Bromide is in group 7, so you know that it's going to have a -1 charge. And for our cesium bromide, we are going to have a chemical formula of CSBr. Please note here, I mentioned the fact we are taking solid cesium bromide and we're dissolving it in water. And so for that, you need to make sure to imply this is solid by putting an S in parentheses afterwards. So once we place it into water, it is going to break up into its ions. And so using that concept, we know there's 1 cesium and 1 bromine, so we know we have to produce 1 cesium ion and 1 bromide ion. So now we know that there is a 1-to-1-to-1 relationship between our cesium bromide, our cesium ions and our bromide ions. So from there, using our dimensional analysis, we can convert from grams of cesium bromide into moles of cesium bromide using the molar mass. Once we know the moles of cesium bromide, we can convert it into moles of cesium by using our one-to-one relationship that we have from our balanced chemical equation. So here we have 78.5 grams going to moles using the molar mass. Then we have moles of cesium bromide going to moles of cesium plus by using the one-to-one relationship determined. And so using the math, plugging into our calculator, I end up with 0.369 moles of cesium plus. So, great thing about these simple, short chemical reactions is if we have a one-to-one-to-one relationship, you figured out everything by just doing one set of math. Because here it's a one-to-one, we also know that that's a one-to-one, so it's going to be the exact same question, same answer. And so even though the question doesn't really ask it, if we have 0.369 moles of cesium plus and 0.369 moles of bromide ions, and we add those together, backwards as it seems, we're going to end up with 0.369 moles of cesium bromide. So, for those of you who are more math-brained people, I probably just gave you a slight migraine. And so what I'm trying to tell you is that 0.369 plus 0.369 equals 0.369. And so one thing that I can try to explain to you, and hopefully it'll alleviate some of the migraine pain, is the fact that these are pieces, this is the entire thing. And so the same idea, if I say in order to create a tricycle, I need 1 seat and 3 wheels. In this situation, this is a piece of the entire complex. This is a piece of the entire complex. And so what I'm saying is I need 0.369 cesium pluses, which would be, again, coming through that portion right there. And then I need 0.369 bromide ions, which again would be that portion right there. And so the entire thing still needs to equal your 0.369. So please do not let this kind of go too math-wise on your brain in the case that you do not want to add these two values together in order to get moles of that. So, let's do another one just to make sure we're on the right page. And so how many moles of each ion are in the following solutions? And so, still same the question, but now we're dealing with 5.0 moles of ammonium sulfate dissolved in water. And so for this one, you have to remember your polyatomic ions. Not only that, you need to remember the charges on your polyatomic ions. And so here we have ammonium. Ammonium is NH4 with a positive charge. Sulfate is an SO4, but it has a 2- charge, or a -2 charge. And so in order to write out the chemical formula properly, we need to make sure that we have 2 ammonium ions for every one of our sulfate ions in the chemical formula. Remember, again, solid because we're placing it into water. As soon as we place it into water, though, we are going to have complete dissociation of this stuff in order to create 2 ammonium ions that are aqueous and 1 sulfate ion that is aqueous. And so now we know that we have a 1-to-2-to-1 relationship between our ammonium sulfate, our ammonium ions, and our sulfate ions. And so the next thing to do is do our same old dimensional analysis. If we start off with 5 moles of ammonium sulfate, we want to convert it into moles of ammonium by using the balanced chemical equation, or the relationship of 1 mole to 2 moles. So we have 5 moles of ammonium sulfate. It will, again, dissociate into 10 moles of ammonium. On the other side, if we have 5 moles of ammonium sulfate, it's in a 1-to-1 relationship with sulfate ions, and so we'd end up with 5.0 moles of sulfate. And so in these cases, you just have to make sure that you remember how to do dimensional analysis. You need to also remember all your polyatomic ions and how to do your nomenclature, because that's usually going to be the first step that is involved in order to do the rest of these problems. And so if you have not already done so, even though if I've talked to you in class and you've talked to me at least at one point in your life, then I have told you repeatedly, you need to do a lot of practice problems. Because this only way that any of this stuff gets any easier is if you do a lot of practice problems and it seems so mundane that you'll pick up the exam and you're like, oh, this is a piece of cake. So please heed my warning now. Do a lot of practice problems. Not just 5 more, but 50 more, 100 more. Do a lot of them.